Gaze up at a clear, dark night far from city lights, and you might just catch a faint, fuzzy patch of light in the constellation of Andromeda. That smudge is an entire galaxy, our closest major galactic neighbor, a swirling island of 1 trillion stars. We often picture galaxies as these brilliant, star-filled disks, but what surrounds them is perhaps even more fascinating. Imagine a vast, spherical cloud, an immense and ghostly halo that envelops the entire galaxy, stretching for hundreds of thousands of light years into the emptiness of intergalactic space. It is not empty. It is a cosmic frontier, a shadowy realm where the conventional rules of a star-filled galaxy seem to break down, and where some of the universe's most peculiar secrets are waiting to be uncovered. What if the most mysterious objects in our entire cosmic neighborhood aren't burning brightly at its heart, but are instead hiding in this faint, sprawling halo? This isn't just a theoretical idea. It's a reality that astronomers are just beginning to map. The halo is a relic of the galaxy's violent history, a graveyard of cannibalized dwarf galaxies, and the birthplace of ancient, wandering stars. It's a place of extremes of profound darkness, punctuated by bizarre, isolated beacons that defy easy explanation. We are about to go on a journey, a voyage of cosmic discovery that will take us far beyond the familiar spiral arms and into this mysterious outer darkness. We will explore the strange and the spectacular, from orphan planets and rogue black holes to stellar corpses that shouldn't exist and enigmatic structures that challenge our very understanding of physics. This video is your guide to 30 of the most peculiar objects ever discovered in the halo of the Andromeda Galaxy. Each one is a story, a cosmic puzzle piece that helps us understand not just our neighbor, but the dramatic and chaotic processes that build galaxies like our own Milky Way. So, let's begin this exploration together and uncover the hidden wonders of the Andromeda Galaxy's halo. Our journey into the halo begins with what should be a familiar sight, a globular cluster. Picture a magnificent, densely packed sphere of 1 million stars, all bound together by gravity, looking like a dazzling swarm of stellar bees. These clusters are typically the ancient seniors of a galaxy, forming in its very earliest days. They are cosmic time capsules, and in the halo, we expect them to be pristine and primitive, composed of the first, pristine hydrogen and helium with very few heavier elements, what astronomers call low metallicity. But the first object on our list, a particular globular cluster in Andromeda's halo, shatters that expectation completely. This cluster is an anomaly, a profound oddball that stands out precisely because it is so rich in heavy elements. Its metallicity is far higher than any halo cluster has a right to be. Think of it as finding a sophisticated, modern metropolis built with advanced technology in the middle of a prehistoric wilderness. It just doesn't belong there according to our standard models. This single observation challenges a cornerstone of our understanding of how galaxies assemble themselves. So, how did this metal-rich cluster end up in the metal-poor halo? The most compelling explanation is as dramatic as it is violent. This cluster likely was not born in Andromeda's halo at all. Instead, it was once the proud centerpiece of a smaller, but more evolved galaxy that Andromeda devoured. Galaxies grow by consuming others, and this cluster is a surviving piece of the victim's core, a celestial trophy from a catastrophic merger billions of years ago. When that smaller galaxy was torn apart, its stars, including this metal-rich cluster, were strewn across Andromeda's halo, left as permanent evidence of a forgotten act of cosmic cannibalism. This anomaly is more than just a strange object. It's a fossil that tells a story of a violent, chaotic past, forcing us to rewrite the history of our nearest galactic neighbor. And if the idea of a star cluster from a devoured galaxy is startling, then the second object on our list will truly challenge your sense of cosmic order. We are taught that the heart of every large galaxy is anchored by a supermassive black hole, a gravitational monster millions or even billions of times the mass of our Sun, reigning from the center of the stellar metropolis. But what if you found one of these behemoths completely untethered, drifting alone in the immense, dark emptiness of the halo? Astronomers have found exactly that, a supermassive black hole with a mass of perhaps 100 million suns, wandering in apparent isolation. For an object so incredibly dense that not even light can escape its grasp, how do you even detect something you cannot see? Its presence was revealed through a phenomenon known as gravitational lensing. The black hole's immense gravitational field warps the very fabric of space-time around it, acting like a colossal, invisible lens. When light from a distant background star passes close to this invisible wanderer, the space-time curvature bends and magnifies that light, causing the star to temporarily and mysteriously brighten in a very specific pattern. It's like watching a lone street lamp in a vast, dark field suddenly flare in brilliance for no apparent reason, only to realize an invisible giant is walking past it, focusing its light with a gravitational lens. Observing this distinct, transient brightening was the telltale signature of a compact, incredibly massive object with no visible host galaxy. The existence of such a solitary titan forces us to confront a dramatic question. How does a supermassive black hole end up as a cosmic castaway, banished from the galactic center that should be its home? The most compelling theory involves the ultimate galactic collision. When two galaxies merge, their central supermassive black holes are thought to eventually spiral toward each other, drawn together by gravity and friction with surrounding gas and stars. As they orbit ever closer, they emit powerful gravitational waves. If a third black hole were involved, perhaps from a previous, smaller merger, the complex gravitational dance could become unstable. In this cosmic slingshot, one of the black holes could be flung out of the newly forming galactic core at tremendous speed, ejected into the outer darkness. This rogue would then travel on a lonely path through the halo, stripped of its kingdom and left to wander the void. An alternative, equally fascinating possibility is that this black hole is not a refugee from a galactic center at all, but is instead the dark, fossilized heart of a galaxy that no longer exists. A small dwarf galaxy, venturing too close to the mighty Andromeda, would have been utterly shredded by tidal forces. Its stars would have been pulled away and assimilated into the halo, but its central black hole, too stubborn and too dense to be easily torn apart, might have been left behind as the sole surviving remnant of its former host. It is a ghost, a silent witness to a galaxy that was completely dismembered billions of years ago. This isolated, supermassive black hole is more than just a strange object. It is direct evidence of the most violent and energetic processes that shape our universe, a permanent scar in the halo from a cataclysm of almost unimaginable scale. Moving from the gravitational ghost of a black hole to another invisible giant, we come to the third strange object, a massive, isolated clump of dark matter. If you thought finding an invisible black hole was difficult, try hunting for something that emits no light, reflects no light, and as far as we know, doesn't interact with light at all. This object is pure gravitational presence, a concentration of mass so significant it warps its surroundings, yet it is completely undetectable by any traditional telescope. Astronomers found this phantom not by seeing it directly, but by observing its profound effect on the light from galaxies that lie far beyond it. As the light from these incredibly distant galaxies travels toward us, it passes through the Andromeda Halo. When that light encounters this dense knot of dark matter, the fabric of space-time itself is bent, causing the light to follow a curved path. The result is that the images of those background galaxies are subtly distorted, stretched, and magnified into faint, tiny arcs, a phenomenon known as weak gravitational lensing. It's like looking at a distant cityscape through the ripples on a hot asphalt road. The images of the buildings are wobbly and warped, telling you something invisible but substantial is affecting the light on its journey to your eyes. What makes this specific dark matter clump so extraordinary and strange is its stark isolation. In our standard model of cosmology, dark matter is the cosmic scaffolding upon which visible galaxies are built. We expect to find vast halos of dark matter, but we also expect that the densest clumps within those halos should have attracted enough ordinary gas and dust over billions of years to form stars, to ignite galaxies, to become visible. This object defies that expectation. It is a naked clump, a massive concentration of dark matter that, for some reason, has failed to gather a visible companion. It exists in a state of pure, dark potential. Its discovery is a critical test for our theories. Some models of dark matter, particularly the cold dark matter model that has long been the standard, predict that the universe should be teeming with such free-floating dark matter subhalos. Finding this one provides strong observational support for that idea. However, its very existence also presents a puzzle. If these subhalos are so common, why don't we see more of them? And why have so many failed to form stars? It could be that the conditions weren't right for gas to cool and collapse within this particular clump, or perhaps fierce cosmic winds from early generations of stars blew the necessary gas away before it could settle. Another, more provocative possibility is that this tells us something fundamental about the nature of dark matter itself. Alternative models, like warm dark matter, suggest that dark matter particles move at higher speeds, which would prevent them from clumping together on such small scales, effectively wiping out these kinds of structures. The fact that we have detected this isolated clump argues against those warmer models and leans toward the colder, slower-moving variety. This invisible knot of mass is therefore more than just an oddity. It is a crucial piece of experimental data in one of the greatest detective stories in modern science, helping us constrain the properties of the mysterious substance that makes up over 80% of the matter in the universe. While we've encountered solitary wanderers and invisible giants, the fourth object in our cosmic tour is a spectacle of pure motion, not a single star, but an entire river of them. Picture a vast, stellar current flowing through the halo, a stream of countless suns all moving together at a breathtaking pace of over 1 million miles per hour. This is a hypervelocity star stream, and its existence points directly to a violent launch from the very heart of the galaxy itself. The origin story of these stellar speedsters is one of celestial dynamics pushed to the extreme. At the center of the Andromeda Galaxy, just like in our own Milky Way, lurks a supermassive black hole, a gravitational titan with the power to fundamentally reshape its surroundings. When a binary star system, two stars orbiting one another, ventures too close to this central monster, a complex and devastating gravitational dance unfolds. The immense tidal forces from the black hole can violently tear the binary pair apart. One of the stars is captured into a tight orbit around the black hole, while the other is flung away, slingshotted outward at an incredible velocity. Now imagine this process happening not just once, but repeatedly over millions of years, with many binary systems meeting the same fate. The result is not just a few individual hypervelocity stars, but a cohesive stream, a cohort of stellar refugees all ejected from the same general region and traveling on similar trajectories out into the halo. These stars become more than just fast-moving points of light. They transform into invaluable cosmic probes. Because they were violently ejected from the galactic center, their paths are not random. They carry with them a kind of memory the precise direction and speed imparted by that initial gravitational slingshot. By meticulously tracing their current positions and velocities backward through time, astronomers can effectively rewind the tape of their journey. This reverse engineering doesn't just point back to the central black hole. It reveals the subtle gravitational influences they experienced along the way. As these stars race through the halo, their trajectories are ever so slightly bent and sculpted by the invisible distribution of mass they pass, the collective pull of dark matter clumps, globular clusters, and the remnants of cannibalized dwarf galaxies. By observing how the stream as a whole has been stretched and distorted over its epic journey, scientists can create a detailed map of the gravitational landscape of the entire halo. It's akin to throwing a handful of glowing confetti into a complex, invisible wind tunnel. By watching how each piece drifts and turns, you can deduce the precise patterns and strength of the unseen airflow. This stellar stream is therefore a dynamic tool, allowing us to weigh the otherwise invisible components of the galaxy and understand the grand architecture of our nearest galactic neighbor in a way that would be impossible through direct observation alone. Following the trail of high-speed stellar rivers, we now encounter a more ghostly presence in the halo, a structure that is less a defined object and more a phantom limb, the lingering echo of a cataclysm that occurred billions of years ago. This is the ghost of a dwarf galaxy, a vast and faint stream of stars that moves in a synchronized, celestial procession through the darkness. Unlike the dense, brilliant core of a living galaxy, this stream is so diffuse and thinly spread that mapping it is like trying to trace the outline of a cloud on a moonless night. Each star in this stream is a sun like our own, but they are separated by vast distances, all sharing a common motion, a shared velocity that marks them as survivors from the same doomed system. This co-moving stream is the final evidence of a galaxy that no longer exists, a cosmic fossil preserved in the immense graveyard of the halo. The story of its destruction is a fundamental tale of how giant galaxies like Andromeda grow. Billions of years in the past, a small, autonomous dwarf galaxy, containing perhaps only a few 100 million stars, was orbiting peacefully in the neighborhood. Its path, however, slowly brought it too close to the immense gravitational pull of the Andromeda Galaxy. As it ventured nearer, the difference in gravitational force between the side of the dwarf galaxy closest to Andromeda and the side farthest away became overwhelming. These tidal forces began to stretch the smaller galaxy, much like the Moon's gravity stretches the Earth's oceans to create tides, but on an infinitely more violent and destructive scale. The dwarf galaxy was literally pulled apart. Over hundreds of millions of years, its stars were stripped away, not in a random explosion, but in a slow, gravitational unraveling. These orphan stars were then flung into wide orbits around Andromeda, where they continue to travel today. Because they were all ripped from the same source, they retain a memory of their original trajectory, forming a long, thin, ribbon-like structure that wraps around the galaxy. This stellar stream is more than just a celestial curiosity. It is a powerful archaeological tool. By carefully measuring the positions, velocities, and even the chemical compositions of these stream stars, astronomers can perform a kind of galactic forensics. They can rewind the clock, tracing the stream's path backward to pinpoint not only where the dwarf galaxy originated, but also when it was destroyed. Each stream is a distinct chapter in Andromeda's autobiography, a timestamp of a past merger event. Furthermore, the specific orbit of the stream is exquisitely sensitive to the gravitational field of the entire halo. As the stream of stars travels through the halo, the invisible hand of dark matter tugs and distorts its shape. By observing how the stream has been warped over time, scientists can map the distribution of dark matter in 3 dimensions, weighing the halo and understanding its shape in a way that is impossible through any other method. These ghostly streams are therefore the ultimate witnesses to the hierarchical build-up of galaxies, providing a tangible record of the countless smaller systems that were consumed to build the majestic spiral we see today. After the ghostly remains of devoured dwarf galaxies, our next discovery shifts from a stellar stream to a complete, yet almost invisible, galaxy in its own right. Drifting in the immense volume of the halo is an object so faint, so ethereal, that it pushes the very definition of a galaxy to its limit. This is an ultra-diffuse galaxy, a cosmic wraith that holds secrets which are completely disproportionate to its nearly imperceptible glow. Imagine a galaxy the size of our own Milky Way, with a similar vast expanse, but containing only 1% of the stars. Those few stars are spread so thinly across that enormous volume that the overall object has an incredibly low surface brightness, making it virtually transparent against the blackness of space. For decades, these ghostly entities floated right past our telescopes, their light so diffuse that it blended seamlessly into the background skyglow. It took advanced, sensitive surveys and meticulous data processing to finally tease their faint signal from the noise, revealing a population of these barely their islands in the cosmic ocean. The mere existence of such a fragile object in the rough neighborhood of a galactic halo is the first part of the mystery. The halo is a dynamic environment, crisscrossed by tidal forces from the main galaxy and littered with the debris of past collisions. How could something so delicate and loosely bound have survived for billions of years without being torn to shreds? The conventional wisdom suggested that all galaxies, even diffuse ones, must be encased within a protective cocoon of dark matter, whose gravity provides the stability to withstand these external forces. But this is where the puzzle deepens into a full-blown cosmic paradox. Measurements of the star's motions within this particular ultra-diffuse galaxy revealed something startling. There is seemingly very little dark matter holding it together. The stars are moving at velocities that can be almost entirely explained by the gravity of the visible stars themselves, with no need for a massive, unseen dark matter halo to bind the galaxy. This finding turns a fundamental principle of galaxy formation on its head. For decades, we've understood that dark matter is the essential scaffolding. It forms the initial gravitational wells that allow ordinary gas to collect, cool, and eventually form stars. A galaxy without dark matter is like a building without a frame. It shouldn't be able to stand up, especially not in a tumultuous environment. So how do we explain this seeming impossibility? Astronomers are actively investigating several compelling theories. One possibility is that this galaxy did have a dark matter halo in the distant past, but it was violently stripped away. A close encounter with Andromeda, or one of its larger satellite galaxies, could have used gravitational tides to pull the dark matter out, leaving behind the more concentrated stars as the sole visible evidence. Another, more radical idea is that this object wasn't born as a traditional galaxy at all. Perhaps it is a tidal dwarf galaxy, a new system that formed from the gas and stars ripped out during a violent collision between two larger galaxies. Since the material for its formation came from the already processed disks of the parent galaxies, which are relatively rich in normal matter and poor in dark matter, the resulting object would naturally inherit that lack of dark matter. This makes it a second-generation galaxy, born from chaos rather than from pristine dark matter clouds. The existence of this dark matter-deficient ghost challenges our most basic assumptions and opens up a new frontier in our understanding of how galaxies can come to be. It forces us to consider that the universe may have more than one recipe for building a galaxy, and some of those recipes are far stranger than we ever imagined. Now, let's shift our focus from these grand structures of stars and dark matter to a far more intimate and beautiful cosmic object, a single, glowing shell of gas adrift in the immense darkness. This is a planetary nebula, the final, spectacular sigh of a dying star. In its death throes, a star like our Sun doesn't go quietly. It pulsates, shedding its outer layers into space in a series of gentle puffs. The exposed, hot core of the star then floods this expanding cloud of gas with intense ultraviolet radiation, causing it to fluoresce in brilliant, ethereal colors. We typically see these celestial butterflies within the bustling stellar nurseries of a galaxy's disk, surrounded by the company of billions of other stars. But the object we've found in the Andromeda Halo is fundamentally different. It is an intergalactic planetary nebula, a lone, glowing orb of ionized gas existing in the profound emptiness between galaxies, a solitary beacon with no visible stellar neighborhood for millions of light years in any direction. Its ghostly, spherical glow is a poignant and isolated monument to a stellar death that occurred in the ultimate solitude. The very existence of such an object immediately raises a profound and haunting question. How did the star that created this nebula end up so utterly alone? There are two leading and equally fascinating theories for its origin. The first is a story of cosmic violence and ejection. The parent star may have once lived a normal life within the crowded disk of the Andromeda Galaxy, perhaps even as part of a binary star system. A close gravitational encounter with other stars near the galactic center, or even with the central supermassive black hole, could have acted like a cosmic slingshot, violently flinging the star out of the galaxy entirely at high speed. This stellar refugee would then have spent the final billions of its life on a solitary journey through the intergalactic void, carrying on until it reached its natural end and expelled its gaseous shroud, leaving this beautiful tombstone to mark its passage far from home. The second possibility is even more mind-bending. This nebula might not be a runaway from Andromeda at all, but rather evidence of an entire, invisible population of stars that permanently reside in intergalactic space. These stars, known as the intraheliostellar population, were likely stripped from small, devoured dwarf galaxies during Andromeda's long history of cosmic cannibalism. When a dwarf galaxy is torn apart, its stars are not all immediately pulled into the main galaxy. Many are scattered into the vast halo, where they orbit independently, isolated from any galactic structure. The star that created this planetary nebula could have been born in one of those dwarf galaxies billions of years ago, lived its entire life in the sparse halo, and died there. In this scenario, the nebula isn't an exile. It's a native of the intergalactic wilderness. This single, glowing bubble of gas, therefore, serves as a unique probe of two different, yet equally dramatic, galactic processes. It is either a direct tracer of the high-velocity ejections that occur in a galaxy's dynamic core, or it is a fossil of the ancient merger events that built the halo itself. By studying its composition and motion, astronomers can hope to distinguish between these origin stories. The chemical fingerprints locked in the glowing gas could reveal whether the star was born from the metal-rich environment of Andromeda's main disk, or from the more primitive, metal-poor gas of a long-vanished dwarf galaxy. Either way, this lone planetary nebula is far more than a pretty picture. It is a solitary clue to the turbulent history and complex structure of the galactic environment it now so beautifully illuminates. Now we arrive at one of the most baffling and energetic phenomena in the entire cosmos, an object not defined by what we can see, but by what we hear, a fleeting, screaming signal from the depths of the void. Our eighth strange object is a repeating fast radio burst source, a cosmic beacon that erupts with unimaginable power from a fixed location deep within the Andromeda Halo. A fast radio burst, or FRB, is a pulse of radio waves that typically lasts for just a few thousandths of a second, Yet in that brief instant, it can release more energy than our sun puts out over several decades. For years, most FRBs were one-off events, mysterious blips that flashed once from the distant universe and were never heard from again, making them nearly impossible to pinpoint and study. But this source is different. It repeats. It crackles to life again and again, sending its powerful, milliseconds-long transmissions from the same precise spot in the halo, giving astronomers a rare and precious opportunity to train their telescopes and try to solve the mystery. The very fact that it is located in Andromeda's halo and not billions of light years further away is the first crucial piece of this puzzle. Its relative proximity on a cosmic scale means we can rule out a vast number of speculative theories that involved even more extreme energies and exotic physics. We know with a fair degree of certainty that this is an object within a galaxy, not a cataclysm on the edge of the observable universe, yet its placement in the halo makes its identity profoundly puzzling. What kind of object, capable of generating such staggering, repeated outbursts, lives in the sparse outskirts of a galaxy, far from the dense stellar environments where we expect to find the most energetic engines? The leading candidate, and the one that currently has the most traction among astronomers, is a specific type of neutron star known as a magnetar. A neutron star is the incredibly dense, collapsed core of a massive star that went supernova, and a magnetar is a neutron star on steroids, possessing a magnetic field, SO Chinese letter, that it is 1,000 trillion times more powerful than Earth's. These fields are under unimaginable strain, and when the crust of the magnetar undergoes a starquake, a sudden, dramatic shift, it can release a titanic amount of energy in the form of a radio burst. This model fits many of the observations, including the raw power and the brief duration of the signals, but the location remains a serious challenge. Magnetars are young objects, the fresh corpses of massive stars. Massive stars have very short lives and are almost always born in the gas-rich spiral arms of a galaxy, where star formation is ongoing. To find one in the ancient, largely star-free halo is like finding a newborn baby in a retirement community. It simply shouldn't be there. So how did it get there? One possibility is that it was, like other halo wanderers, kicked out of the galactic disk. The supernova explosion that created the magnetar could have been asymmetrical, giving the newborn neutron star a powerful kick that sent it racing out of the crowded disk and into the halo at hundreds of thousands of miles per hour. It now resides in its lonely exile, still periodically cracking its powerful magnetic whip. Another, more exotic theory points to a different kind of origin story. Perhaps this magnetar is not a recent escapee, but a very old object that was born in a globular cluster. These dense clusters of ancient stars, which orbit in the halo, can sometimes form exotic binary systems. Collisions or complex interactions between stars in these crowded environments could potentially create a magnetar, which then remains within the cluster's gravitational grasp, explaining its presence far from the star-forming disk. Beyond the magnetar hypothesis, the repeating nature of the bursts opens the door to other, even more speculative ideas. Could this be evidence of an advanced extraterrestrial civilization? While scientists are rightly skeptical of leaping to such a conclusion, the possibility cannot be entirely dismissed from a theoretical standpoint. An incredibly powerful, focused transmitter, perhaps driving a light sail spacecraft across interstellar distances, could produce a signal that looks very much like a fast radio burst. However, the sheer, raw energy required makes this a less favored explanation. It would require a civilization harnessing the total power output of an entire planet, focused into a single, fleeting beam. The fact that this source is repeating and located in our own galactic backyard makes it one of the most important astronomical discoveries of recent years. It is a natural laboratory for studying one of the universe's most energetic and poorly understood processes. Every time it bursts into activity, it provides another data point, another clue that helps us narrow down the physics of these incredible events. Whether it is a kicked magnetar, a relic from a globular cluster, or something entirely new, this repeating radio screamer in the halo forces us to expand our understanding of where and how nature can create such spectacular displays of raw power. Nestled among the ancient, typically pristine stars of the halo, astronomers have discovered a population of cosmic gems with a surprisingly rich chemical signature stars that are overflowing with carbon. These are not your average metal-poor halo stars. They are carbon stars, celestial objects whose atmospheres contain more carbon than oxygen, a peculiarity that leads to the formation of soot and complex carbon molecules in their outer layers, giving them a characteristically deep red hue. Finding such chemically complex stars in the halo is like discovering a collection of intricate, modern sculptures in a prehistoric cave. It immediately raises the question of how such advanced chemistry arose in an environment thought to be composed of the universe's most primitive, simple ingredients. These stars are true relics, and their very atmospheres act as a fossil record, preserving the chemical conditions of the era in which they formed over 10 billion years ago. In the early universe, the only elements were hydrogen, helium, and trace amounts of lithium. Every heavier element, every atom of carbon, oxygen, and iron that makes up our world and our bodies was forged in the nuclear furnaces of stars and scattered across space by their violent deaths. The first generations of stars to form after the Big Bang were responsible for this initial chemical enrichment, and the halo of a galaxy like Andromeda is supposed to be dominated by the descendants of these first stars, which should be very poor in heavy elements. The existence of a significant population of carbon-rich stars tells a more nuanced and fascinating story. It suggests that even in those very early times, certain stellar processes were incredibly efficient at producing and distributing carbon, effectively seeding specific regions of the nascent halo with this fundamental building block of life. The primary factory for these carbon stars is believed to be a specific type of ancient, low-mass star in its final evolutionary stages. As these stars aged, they underwent a process known as dredge-up, where convection currents from the deep interior brought the products of nuclear fusion, primarily carbon, up to the surface. When these stars then gently shed their enriched outer layers through stellar winds, they polluted the surrounding interstellar gas with a distinct chemical signature, rich in carbon but relatively poor in other heavy elements like iron. The next generation of stars that formed from this polluted gas would then inherit this unusual carbon-rich fingerprint, becoming the carbon stars we observe today. So, the presence of these stars is direct evidence of this specific form of chemical pollution from the very first stellar generations. However, the real mystery and the reason this is a true anomaly lies in their patchy, unexpected distribution. They are not spread evenly throughout the halo. Instead, they are found clustered together in specific, vast clouds and streams, often coinciding with the stellar debris of cannibalized dwarf galaxies. This clustering is the crucial clue that challenges our models of halo formation. The traditional, monolithic model suggested the halo formed from a relatively smooth, spherical collapse of primordial gas, which would have led to a much more uniform chemical mix. The clumpy distribution of carbon stars tells a far more violent and chaotic story. It strongly supports the hierarchical model of galaxy formation, where giant galaxies like Andromeda are built over time from the mergers and accretion of countless smaller systems. In this scenario, these carbon stars were not born in the main Andromeda halo itself. They were likely formed within distinct, small dwarf galaxies that evolved on their own independent timelines. Within the sheltered environments of these dwarf galaxies, unique chemical enrichment histories unfolded, allowing for the efficient production of carbon in certain regions. When Andromeda eventually consumed these smaller galaxies, it didn't just absorb their stars, it absorbed their distinct chemical identities, strewing these carbon-rich fossils along the orbital paths of their former homes. The halo, therefore, is not a single, chemically homogeneous entity. It is a mosaic, a layered archaeological site where each stream and cluster of stars tells a different chapter of the galaxy's assembly history. By mapping the precise locations and chemical compositions of these carbon stars, astronomers can perform a kind of galactic genealogy, tracing them back to their original, long-vanished parent galaxies and reconstructing the timeline of the mergers that built the Andromeda we see today. From the enigmatic repeating radio bursts, we turn to an event of even more staggering, instantaneous power, a gamma-ray burst. These are the most luminous explosions in the universe since the Big Bang itself, cosmic flashbulbs that for a few fleeting seconds can outshine every other source of gamma rays in the cosmos combined. They are typically the death cries of the most massive stars, signaling the birth of a black hole or the collisions of ultra-dense stellar remnants like neutron stars. What follows the initial blast of gamma rays is an afterglow, a fading emission across other wavelengths like X-ray, optical, and radio, caused by the expanding shockwave of the explosion plowing into the surrounding interstellar medium. It is this afterglow that allows astronomers to pinpoint the location of the burst with extreme precision and, crucially, to identify its host galaxy. Which brings us to our 10th strange object, a long-lasting gamma-ray burst afterglow that was traced directly to the halo of the Andromeda Galaxy, yet it appeared to be completely isolated, a brilliant flare with no host galaxy in sight. This was an orphan afterglow, a cosmic explosion that seemed to have happened in the middle of nowhere. The implications of this solitary detonation are profound. If a gamma-ray burst marks the death of a very massive, short-lived star, then such a star must have been born somewhere. Massive stars form in the dense, gas-rich environments of galactic disks, and they simply do not have the time to wander far from their stellar nurseries before exploding. Finding one in the sparse, ancient halo is like finding a lit stick of dynamite floating in the middle of the ocean. It forces you to ask how it possibly got there. Astronomers have developed two primary theories to solve this puzzle, each telling a very different story about stellar motion and cosmic violence. The first scenario is one of dramatic ejection. The progenitor star, a true behemoth, may have been born in the bustling disk of Andromeda, perhaps as part of a tight binary or multiple star system. A close gravitational encounter with other stars in a dense cluster, or even a slingshot interaction with the central supermassive black hole, could have violently ejected the star from its birthplace at hundreds of thousands of miles per hour. This stellar rebel would then have spent the remaining few million years of its life on a high-speed journey out of the galactic plane and into the halo. When its core finally collapsed, it did so in utter solitude, its gamma-ray burst and the ensuing afterglow flaring in the darkness far from any visible galactic structure. In this story, the orphan afterglow is a tracer of the most extreme stellar kinematics, a testament to the fact that galaxies can literally fling their most massive stars into the void. The second possibility is even more intriguing and suggests we may be witnessing a completely new class of cosmic explosion. Perhaps this was not a standard long gamma ray burst from a collapsing massive star at all. The longevity and behavior of its afterglow could be explained by the merger of two incredibly dense objects, like a neutron star and a black hole, or two neutron stars. Such mergers are also thought to produce short gamma ray bursts, but the exact properties depend on the masses involved and the environment. These compact object binaries can be kicked out of their host galaxies during the supernova explosions that created them, and they have billions of years to slowly spiral together and merge far from their original home. The halo, with its vast volume and history of galactic cannibalism, could be sprinkled with such exiled binary systems. When they finally coalesce, their explosion would appear as an isolated event, unmoored from any visible galaxy. This interpretation challenges our existing classification of gamma-ray bursts and suggests that the halo could be a hiding place for a population of exotic, wandering compact binaries that we have only just begun to detect. This single, lonely afterglow, therefore, acts as a critical piece of evidence in our understanding of stellar life cycles and the dynamic processes that can scatter stellar corpses across the galaxy. By analyzing the precise light curve and spectrum of the fading emission, scientists can hope to distinguish between a collapse of a massive star and a merger of compact objects. The chemical fingerprints in the afterglow could reveal the environment the explosion occurred in, potentially showing whether it was the pristine, metal-poor gas of the halo or carried the enriched material of the galactic disk with it. This orphan event is more than just a flash in the dark. It is a unique probe of stellar death, galactic dynamics, and perhaps even a window into a previously hidden class of cosmic cataclysms. Moving from solitary explosions and stellar oddities, we now encounter a pair of cosmic changelings, two objects that appear to be galaxies, but were forged in a completely different celestial fire. These twin tidal dwarf galaxy candidates represent one of the most fascinating processes in galactic evolution. Unlike the vast majority of galaxies, which form from the top-down collapse of primordial dark matter clouds, these two are thought to be second-generation objects, built not from pristine gas, but from the wreckage of a violent collision. The story of their birth begins with a cataclysmic merger between two larger galaxies in Andromeda's distant past. As these galaxies tore into each other, their mutual gravitational pull drew out vast, filamentary tails of gas, dust, and stars, cosmic flotsam, ejected into the intergalactic void by the immense tidal forces. Within these ejected streams of material, something remarkable happened. Dense knots of gas within the tidal tails began to collapse under their own gravity, triggering intense, localized bursts of star formation. These newborn stellar systems, complete with their own independent gravitational pull, are what we now observe as these two candidate galaxies within the halo. Their properties are what make them so distinct and so telling. They tend to be unusually rich in heavy elements because the gas they formed from was not primordial. It had already been processed through previous generations of stars within the disks of their parent galaxies. This gives them a chemical maturity that stands in stark contrast to the ancient, metal-poor dwarf galaxies that typically populate the halo. Furthermore, they are expected to be almost completely devoid of dark matter. Since they formed from collisional debris that was pulled from the already shock-heated and disturbed disks of the parent galaxy's disks, which are themselves dominated by normal, baryonic matter, they simply didn't have access to the dark matter halos that surround primordial galaxies. This single characteristic is what makes them such profound challenges to our definitions. If a defining feature of a galaxy is that it forms within and is gravitationally dominated by a halo of dark matter, then are these objects truly galaxies at all? They are self-gravitating collections of stars and gas. They can have their own satellite systems, and they can persist for billions of years, yet they lack the very scaffolding we thought was essential for their existence. Finding them in the halo of Andromeda is exceptionally rare and significant because it provides a direct, observable test of this entire formation theory. Their existence confirms that galaxy formation is not a one-way street. It's a cycle of destruction and rebirth, a major galactic collision, an event of pure chaos and devastation, can actually become a creative force, giving rise to new, independent stellar systems far from the scene of the original crash. By studying these twins, astronomers can look for the subtle chemical signatures that would confirm their origin from pre-enriched gas, and they can meticulously measure the motions of their stars to confirm the predicted lack of a significant dark matter component. Each one is a living fossil of a single, specific ancient collision, allowing us to not only confirm our models of galactic interactions, but to precisely date when that merger occurred, adding another crucial piece to the intricate archaeological timeline of how Andromeda came to be. Deeper still, in the halo's shadowy expanse, we encounter a trio of the most ghostly structures imaginable, 3 ultra-faint dwarf spheroidal galaxies. To call them galaxies almost feels like an exaggeration. Each one is a wraith, a collection of so few stars, just a few thousand perhaps, that if you were standing on a planet in one of them, the night sky would appear almost completely black, punctuated by only a handful of faint, neighboring suns separated by vast, light-years-wide gulfs of emptiness. They are the faintest, most ethereal galaxies we have ever discovered, so dim that their total light output is often less than that of a single bright giant star in our own Milky Way. Finding them is an astronomical triumph, requiring painstaking analysis of the deepest, most sensitive sky surveys to tease out their sparse, ancient starlight from the background glow of the cosmos. Yet, for their profound faintness, these 3 siblings hold immense cosmic weight because they are not merely collections of stars. They are the most dark matter-dominated objects known in the entire universe. The ratio of dark matter to visible matter in these systems is staggering, dwarfing even the proportions found in giant galaxies like Andromeda. This means that the few thousand ancient stars we can see are merely tracers, insignificant sparks adrift in a colossal, invisible ocean of dark matter, their motions entirely governed by the gravitational pull of this unseen behemoth. Studying these ultra-faint dwarfs is the closest we can come to directly observing the raw building blocks of the cosmos. They are considered pristine relics, living fossils from the dawn of time. The stars within them are among the oldest in the universe, composed almost entirely of hydrogen and helium, with only the faintest sprinkling of heavier elements forged in the first generations of exploding stars. They represent a primordial galaxy type, the minimal structures that first lit up after the cosmic dark ages. By analyzing their chemical compositions, astronomers are effectively reading a chronicle of the universe's earliest star formation, a story written in the pristine atmospheres of these ancient suns. This makes each of these 3 faint smudges a unique window into the conditions of the infant universe, a direct portal back over 13 billion years. Their very existence in Andromeda's halo, however, presents one of the most persistent puzzles in modern cosmology, known as the too big to fail problem. According to sophisticated computer simulations of dark matter behavior, the halo of a galaxy like Andromeda should be teeming with hundreds of such dense, dark matter subhalos. Yet, we only observe a handful of these ultra-faint dwarfs. So, where are all the others? The simulations suggest these subhalos should be massive enough and have enough gravitational pull to attract gas and form stars, becoming visible dwarf galaxies. The fact that we see so few implies that something is preventing star formation in the vast majority of them. One leading theory is that the intense ultraviolet radiation from the first stars and galaxies, a phenomenon known as cosmic reionization, heated the intergalactic gas early in the universe's history, making it too energetic to collapse into the small, shallow gravitational wells of these potential dwarfs. Essentially, the cosmic environment was too hostile for these faintest of galaxies to ever light up. The 3 we do see might be the rare, fortunate survivors that managed to form their handful of stars just before the cosmic lights turned on. Or perhaps they formed in slightly denser patches of dark matter that could hold onto their gas against the onslaught. Another, more tantalizing possibility is that this discrepancy tells us something fundamental about the nature of dark matter itself. The standard cold dark matter model predicts an abundance of small-scale structure. If these subhalos are truly missing, it might be evidence for a warmer type of dark matter, where particles move at higher speeds. This warmer dark matter would have suppressed the formation of such small clumps in the early universe, resulting in a halo population that more closely matches what we actually observe. The survival of these three specific dwarfs within Andromeda's immense gravitational grip adds another layer to the mystery. They are incredibly fragile, held together by a dominant, but not infinitely strong dark matter halo. One might expect that the tidal forces from Andromeda, the same forces that shred larger dwarf galaxies into stellar streams, would have long ago torn these ultra-faint systems completely apart. The fact that they persist suggests that their dark matter halos are exceptionally robust and centrally concentrated, acting as a kind of immutable gravitational anchor that allows them to withstand the galactic tides. Each of these three faint specks of light is therefore a critical natural laboratory. They are testing grounds for our theories of galaxy formation, probes of the early cosmic environment, and crucial constraints on the very properties of the mysterious dark matter that shapes the entire universe. Streaking through the halo's darkness like a cosmic bullet, our 16th object is a beacon of pure velocity, a runaway pulsar. This is no ordinary star. It's the collapsed, ultra-dense core of a once massive sun that ended its life in a supernova explosion. Now it's a neutron star, a city-sized object so incredibly compact that a single teaspoon of its material would weigh billions of tons. But what makes this particular neutron star a pulsar is its mind-bending spin. It rotates dozens or even hundreds of times every single second. With each rotation, it sweeps a powerful, focused beam of radio waves and other radiation across space, much like the frantic, spinning beam of a celestial lighthouse. From our vantage point, each time that beam flashes across the Earth, our telescopes detect a pulse of energy, an incredibly regular tick-tock that marks the passing milliseconds with a precision that rivals atomic clocks. This rapid, rhythmic pulsing is what first revealed its presence, but what truly sets this pulsar apart is its motion. It isn't just spinning, it is flying through the halo at an astonishing speed, a significant fraction of the speed of light, on a solitary path that will eventually carry it out of the Andromeda Galaxy entirely and into the cold, intergalactic void. To achieve such an incredible velocity, its birth must have been a cataclysm of unimaginable violence. The story begins with the death of its progenitor, a massive star that had exhausted its nuclear fuel. When the star's core could no longer support its own immense weight, it catastrophically collapsed in upon itself in a fraction of a second, triggering a titanic shockwave that blew the star's outer layers into space in a supernova explosion. However, this explosion was not a perfectly symmetrical event. For a brief, critical moment, a powerful avalanche of neutrinos near massless, ghostly particles can be ejected more forcefully from one direction of the collapsing core than another. This creates a tremendous rocket effect, literally kicking the newborn neutron star in the opposite direction. It's as if the star itself was shot out of a cannon, recoiling from its own violent birth. An alternative, or perhaps complementary, kick could come from slight asymmetries in the supernova explosion itself. If more stellar material is ejected from one side of the star, the conservation of momentum will send the dense remnant hurtling in the opposite direction. This is the cosmic equivalent of throwing a grenade and having the casing fly backward. The The neutron star is the shrapnel from its own detonation. The result is a stellar corpse flung across space, its lighthouse beam cutting a lonely path through the halo. This runaway pulsar is more than just a fascinating oddity. It serves as a unique probe of the extreme physics that govern stellar deaths. By measuring its speed and trajectory, astronomers can effectively work backward to model the forces at play in that initial, split-second supernova kick, offering insights into processes that are otherwise impossible to observe directly. Furthermore, its journey through the halo allows it to act as a scout. As it travels, its rapid pulses are incredibly stable, but the tenuous wisps of gas in the halo can cause minute-measurable delays in the arrival time of these pulses. By analyzing these subtle shifts, scientists can map the density and distribution of the nearly invisible interstellar medium in the halo, charting a course through the galaxy's most remote territories using this natural, high-speed probe. Deep within the faint, sprawling reaches of the halo, astronomers have mapped a structure so vast and ethereal it defies easy categorization, a Lyman alpha blob. This object is not a collection of stars, nor a swirling disk of gas. It is an immense, cloud-like nebula on a truly cosmic scale, often hundreds of thousands of light years across, glowing with a specific, singular hue of ultraviolet light known as Lyman alpha radiation. This distinct glow is the signature of hydrogen gas, the universe's most fundamental element, being energized and made to shine. While Lyman alpha blobs have been observed in the distant, early universe, finding one here, nestled within the halo of Andromeda, is deeply puzzling. In the remote depths of intergalactic space, far from the bustling stellar nurseries of the main galaxy, what mysterious engine could possibly be powerful enough to light up such an enormous volume of gas, causing it to fluoresce like a ghostly beacon in the void? The leading theory points to a frenzy of stellar birth. Within the heart of this colossal cloud, there could be a hidden, massive region of intense star formation, a stellar nursery operating on an almost unimaginable scale. Here, countless new, hot, massive stars would be igniting, each one flooding its surroundings with fierce ultraviolet radiation. This energetic light strikes the surrounding hydrogen atoms, energizing them and causing them to re-emit that energy as the characteristic Lyman alpha glow, illuminating the entire vast structure from within. It's like a city so immense that its collective streetlights illuminate the entire cloud layer above it, making the entire weather system glow. The sheer scale of the blob suggests this wouldn't be just a single large cluster, but potentially an entire nascent dwarf galaxy in the process of forming, its birth shrouded in a colossal incubator of glowing gas. However, the extreme isolation presents a problem. Such intense starbursts usually require a rich reservoir of cool, dense gas to fuel them, the kind typically found within a larger galactic structure, not drifting alone in the metal-poor halo. An alternative, and even more powerful, explanation involves a hidden monster, a quasar. At the very center of this glowing cloud, there could be an active, supermassive black hole, voraciously feeding on surrounding gas and dust. As matter spirals inward at near light speed, it forms a searingly hot accretion disk that can outshine every star in a galaxy combined, emitting a torrent of ultraviolet and X-ray radiation. This incredible energy output could be more than sufficient to light up the entire surrounding hydrogen cloud, creating the Lyman alpha blob we see. In this scenario, the blob is the illuminated fuel supply for a ravenous cosmic engine, a signpost for a hidden gravitational pit that is actively consuming matter on a colossal scale. Yet, the quasar itself might be shrouded by thick clouds of dust, hiding its brilliant core from our direct view and leaving only the glowing gas cloud as evidence of its presence. A third and more subtle possibility challenges the need for an external power source altogether. This theory suggests the glow could be caused by a process known as gravitational cooling. Imagine a massive inflow of pristine, primordial gas drawn into the halo from the intergalactic medium over billions of years. As this vast cloud collapses under its own gravity, the gas particles pick up speed and crash into one another, converting their gravitational potential energy into heat. To cool down and continue collapsing, the cloud must radiate this energy away, and one of the most efficient ways for simple hydrogen gas to do that is by emitting Lyman alpha radiation. In this case, the blob's glow isn't a sign of being lit up by stars or a quasar, but is instead the intrinsic signature of the cloud's own birth and condensation, a luminous sigh as it settles into the halo. Each of these theories paints a dramatically different picture of the blob's nature and its role in the galactic ecosystem. Is it a cradle for a new galaxy, the cloak for a hidden quasar, or a simple, cooling cloud of primordial gas? The answer likely lies in a detailed analysis of its spectrum, looking for the faint chemical fingerprints that would betray the presence of hot young stars or the hard radiation field of an active black hole. This single, glowing structure therefore acts as a critical diagnostic tool, its very existence challenging our understanding of how gas behaves, cools, and forms stars in the most remote and unexplored territories of a galaxy. Our next object is a cosmic illusion of breathtaking perfection, a phenomenon so rare and elegant it was predicted by Einstein's theory of general relativity long before we ever had the telescopes to see it. Drifting within the halo is a perfect Einstein cross, a celestial mirage where a single, intensely bright object from the far distant universe, a quasar billions of light years behind Andromeda, appears to us not as one point of light, but as four, arranged in a symmetrical cross around a central, faint smudge. This stunning configuration is not magic. It is the ultimate demonstration of gravity's power to warp the very fabric of reality. The foreground object, which resides within Andromeda's halo, acts as a gravitational lens. Its mass, whether visible or invisible, creates a dip in space-time, and when the light from the background quasar travels toward us, its path is bent as it passes through this warped region, much like light bending through a lens of glass. In this specific, perfectly aligned case, the lensing is so symmetrical that it splits the single quasar's light into multiple distinct paths, creating the four brilliant images we see. That central, faint smudge is the lensing object itself, the foreground galaxy or cluster, whose gravity is engineering this entire spectacular display. The true power of this cosmic cross lies not in its beauty, but in its function as a natural scale. By measuring the precise separation between the four quasar images and by studying their individual brightness, astronomers can perform a direct calculation of the total mass of the lensing object in the foreground. It's a celestial balancing act. The more massive the lens, the wider the separation of the images. This technique allows scientists to literally weigh the lensing object with incredible precision, regardless of whether it is emitting any light of its own. So, what exactly is this cosmic lens hiding in Andromeda's halo? The prime suspect is an ultra-compact, massive star cluster, a globular cluster so dense and packed with stellar mass that its collective gravity is powerful enough to create such a defined lensing effect. Confirming this would tell us that some globular clusters in the halo are far more massive than they appear, potentially harboring significant amounts of unseen stellar remnants like neutron stars and black holes within their cores, or even a large quantity of dark matter. However, there is another, more mysterious possibility. The lensing object could be a virtually pure, isolated knot of dark matter, a sub-halo so dense that it can produce strong gravitational lensing, yet one that has mysteriously failed to attract any significant number of stars to make it visible. Finding such a dark lens would be a monumental discovery, providing a uniquely clean laboratory to study the properties of dark matter without the complicating glare of stars and gas. The Einstein cross is therefore far more than a pretty picture. It is a precision instrument. Every time the background quasar flickers, and quasars are notoriously variable, that flicker appears in each of the 4 images at a slightly different time. The delay between the arrival of the same flicker in one image versus another is exquisitely sensitive to the detailed distribution of mass within the lens. By meticulously timing these delays, astronomers can map the lens's mass distribution in 3 dimensions, discerning whether the mass is smoothly spread out or clumped in ways that could reveal the presence of individual, massive objects like stellar black holes within the cluster. This single, beautiful alignment in the halo acts as both a scale and an X-ray machine, allowing us to peer into the internal structure of a distant object and weigh the invisible components of our universe with a precision that no human-made instrument could ever hope to achieve. But as we have seen, the halo is not a chemically uniform place. It's a chaotic mix of old and new, primitive and enriched. This brings us to a star that represents the purest, most ancient end of that spectrum, a true cosmic fossil. Object number 19 is a solitary ancient sun with an incredibly low metal content, so pristine that its atmosphere serves as a direct, unaltered sample of the early universe's composition. When astronomers measure the chemical makeup of a star, they are reading a history book. Most stars, even ancient ones, contain a small but significant amount of elements heavier than hydrogen and helium, what they call metals. These elements were forged inside previous generations of stars and scattered by their explosive deaths, enriching the cosmic gas from which new stars would later form. This particular star, however, is a profound exception. Its metallicity is millions of times lower than that of our Sun. It is composed of almost nothing but the primordial hydrogen and helium created in the Big Bang itself, with only the faintest possible trace of anything else. Finding such a star is like uncovering a perfectly preserved archaeological artifact, a single drop of water from the original cosmic ocean that has remained untouched for over 13 billion years. Its chemical fingerprint is a direct window into the conditions of the universe before the first stars ever ignited, a snapshot of the pristine raw material from which everything we see today was ultimately built. The existence of such a metal-poor star challenges our understanding of the very first stellar generations. Theoretical models suggest that the very first stars, known as population 3 stars, were behemoths, hundreds of times more massive than our Sun. These giants would have lived fast and died young, exploding as supremely powerful supernovae that polluted the surrounding gas with the first heavy elements. The fact that we can still find stars with almost zero metals implies that not all of the early universe's gas was immediately enriched. There must have been pockets of pristine gas that managed to avoid this first wave of pollution, pockets that lingered long enough to collapse and form a second generation of stars, of which this object is a surviving member. This star is therefore a living relic from the era before the cosmos was chemically complex, a messenger from a time when the universe was a much simpler, but far more extreme, place. By studying its precise composition, even the vanishingly small amounts of elements like carbon or iron, astronomers can work backwards. They can infer the properties of the very first supernova that must have eventually, and ever so slightly, contaminated its birth cloud. The specific ratios of elements in its atmosphere act as a forensic signature, telling us about the mass and explosion energy of those long-vanished first stars. This single point of light in the Andromeda Halo is more than just an old star. It is a time capsule, offering us a unique and precious glimpse into the dawn of cosmic time, and the mysterious first chapter of star formation. Yet even these singular beacons and brilliant mirages are only small components within a far grander, more pervasive structure that envelops the entire galaxy. If we shift our observational eyes from optical telescopes to instruments that see the high-energy universe, the entire character of the Andromeda Halo transforms. It is not a dark, empty void, but is instead filled with a faint, colossal sphere of gas, heated to temperatures of millions of degrees. This is the extended X-ray halo, a diffuse and seething ocean of multimillion-degree plasma that stretches for hundreds of thousands of light years, detected only by the specific, high-energy X-ray radiation it emits. The sheer existence of this hot gaseous envelope tells a story of continuous, violent energy input on a galactic scale. The primary engine for this heating is believed to be the collective fury of countless supernova explosions occurring within the galactic disk over billions of years. Each time a massive star dies, it doesn't just vanish. It blows a titanic bubble of hot, metal-enriched gas out into its surroundings. These supernova winds, driven by the incredible energy of the blast, can collectively create a vast galactic fountain, ejecting material out of the star-forming disk and into the halo at tremendous speeds. As this hot gas travels outward, it expands and cools, but the sheer volume and constant recurrence of these events, combined with the accretion of even hotter gas falling into the galaxy from the intergalactic medium, acts like a giant, galaxy-wide heater, maintaining the halo's immense temperature. This creates a dynamic, circulating flow where material from the disk is constantly being vented into the halo, while cooler gas from the halo is supposed to eventually rain back down onto the disk to fuel new generations of stars. Herein lies the profound mystery that astronomers are still working to solve. According to our basic understanding of physics, a gas this hot, but also this diffuse, should radiate away its energy very efficiently in the form of X-rays. As it loses energy, it should cool down. As it cools, the atoms should slow their frantic motion, allowing gravity to take over, pulling the gas back inward in a process known as a cooling flow. This cool, dense gas should then be the perfect raw material to collapse and form new stars, either in the halo itself or as it falls back to the disk. Yet, when we look at the halo, we see a glaring absence of this cooling gas and the vigorous star formation it should trigger. The hot gas remains hot, stubbornly refusing to cool and collapse in the quantities our models predict. This cooling flow problem suggests that some hidden, continuous energy source is constantly reheating the halo's gas, preventing it from settling down. It's as if you had a pot of water sitting on a stove, constantly boiling and sending off steam, but never actually boiling dry because some unseen flame is always replenishing the heat. So, what is this mysterious furnace? One leading candidate is a process called gravitational heating. As the galaxy continuously draws in fresh, pristine hydrogen gas from the vast filaments of the cosmic web, this material is falling into the immense gravitational well of the halo. As it plummets inward, it picks up tremendous speed, converting its gravitational potential energy into kinetic energy. When this fast-moving gas finally collides with the halo's existing atmosphere, the resulting shock waves act like immense sonic booms, dumping enormous amounts of heat back into the plasma and offsetting the energy lost through X-ray radiation. Another, more dramatic possibility involves the supermassive black hole at Andromeda's center. While it may be quiet now, it likely had active periods in the past. During these quasar phases, the black hole would have blasted out colossal jets of energy and bubbles of ultra-hot plasma that traveled far out into the halo. These eruptions could have provided a massive, one-time injection of heat that still resonates through the halo today, or they could occur in repeated, smaller outbursts that provide the necessary periodic heating. There is also the possibility that the energy comes from the sheer cumulative power of stellar winds and supernovae from stars that were themselves born in the halo, perhaps within the globular clusters or the shredded remains of dwarf galaxies. The extended X-ray halo is therefore not a static shroud. It is a dynamic and balancing act. It is a testament to the constant struggle between the forces of gravity, which want to pull everything together, and the powerful, often hidden energy sources that keep the galaxy's vast atmosphere hot, diffuse, and largely infertile. Understanding this equilibrium is key to understanding the life cycle of galaxies, dictating how they grow, how they fuel future star formation, and ultimately, how they evolve over cosmic time. As we step back from individual objects and look at the stellar halo as a whole, we find that its very shape tells a dramatic story. You might expect this vast cloud of stars to be a perfect, symmetrical sphere surrounding the galaxy, but detailed observations reveal something quite different. The stellar halo of the Andromeda Galaxy is profoundly lopsided, a cosmic blob that stretches much farther in one direction than in others. This asymmetry is not a flaw or an accident. It is a direct, fossilized imprint of the galaxy's cannibalistic history, a lasting monument to the violent events that built it over billions of years. The shape of the halo acts like a celestial crime scene, and the evidence points overwhelmingly to a recent, colossal feast. The prevailing theory is that this large-scale distortion was caused by the relatively recent accretion of a single, substantial dwarf galaxy. When such a galaxy is torn apart by Andromeda's immense gravity, its stars are not scattered randomly. Instead, they are stripped away along the victim's orbital path, forming long, coherent streams that slowly disperse over cosmic time. If the devoured galaxy was particularly massive and its assimilation happened only a few billion years ago, a recent event on a galactic timescale, the debris from that single event can dominate the entire large-scale structure of the halo, creating the pronounced lopsidedness we observe today. It's as if we are seeing the last giant splash from a rock thrown into a pond, its ripples still defining the shape of the water's surface long after the impact. By carefully mapping the density of stars in the halo and tracing the subtle patterns of their motions, astronomers can work backwards. They can identify the specific orbital plane of that ill-fated dwarf galaxy, effectively determining the direction from which it was consumed. This is galactic paleontology. The halo's asymmetry is a fossilized orbit, permanently recording the trajectory of a long-vanished system in the grand architecture of its conqueror. This discovery fundamentally challenges older, simpler models of galaxy formation, which suggested halos formed from a smooth, spherical collapse of primordial gas. The lopsided halo provides overwhelming support for the hierarchical model, where giants like Andromeda are assembled piece by piece through a violent, chaotic process of mergers and acquisitions. The fact that the asymmetry is so pronounced suggests that this building process is not over. Andromeda is likely still digesting this last large meal, and its halo remains dynamically active and unsettled. This ongoing transformation has profound implications for our own galactic future. The Andromeda Galaxy is on a collision course with our Milky Way, and the structure of its halo gives us a preview of the forces that will shape that eventual merger. Understanding the lopsided nature of Andromeda's halo allows us to better model its total mass and gravitational field, which in turn refines our predictions for the complex dance that will unfold when our two galaxies finally meet. The halo's shape is therefore more than just a historical record. It is a key to forecasting the next great chapter in the life of our local galactic group. Wrapping far around the outer fringes of the halo, astronomers have mapped a structure of such immense scale that it challenges our very perception of a galaxy's boundaries. This is a vast, ring-like stream of stars, a great circle of stellar debris that orbits at an incredible distance from Andromeda's bright center. Its discovery was a feat of modern astrophysics, requiring the painstaking assembly of data from wide-field sky surveys to connect the dots between sparse, ancient suns and reveal the faint, colossal pattern they trace across the sky. This structure bears a striking resemblance to a feature in our own cosmic backyard, known as the Monoceros Ring, a similar band of stars encircling the Milky Way. Finding a parallel structure in Andromeda's halo is profoundly significant. It suggests that the process which created it is not a unique fluke, but a fundamental and recurring mechanism in the evolution of large spiral galaxies. The dominant theory explaining this great circle is a story of gravitational destruction and cosmic artistry. The leading idea is that we are witnessing the final, stretched-out remains of a dwarf galaxy that ventured too close to Andromeda billions of years ago. This smaller system, perhaps similar to one of the faint spheroidal dwarfs we see today, was captured by the giant galaxy's immense gravitational pull. Over countless orbits, the difference in gravitational force between the near and far sides of the dwarf galaxy, the tidal force, slowly and inexorably pulled it apart. This wasn't a sudden explosion, but a gradual gravitational unraveling. The stars of the victim galaxy were stripped away from it not randomly, but in a continuous stream, much like sand grains trickling from a hole in a bag swung in a circle. The result is that the stars from the disrupted galaxy now follow orbits that are almost identical to the path of their parents' final journey, forming a long, thin, ribbon-like structure that appears to us as a vast ring. This phenomenon is known as a tidal stream, and its circular nature is a direct fossil of the original orbit of the devoured dwarf. The specific geometry of this great circle holds a treasure trove of information. By modeling the precise shape and density of the stream, astronomers can rewind the clock, tracing the orbits of these stars backward in time to pinpoint not only the original mass of the dwarf galaxy, but also the exact moment of its disruption. This ring acts as a cosmic clock, dating a specific accretion event in Andromeda's history. Furthermore, the stream's structure is exquisitely sensitive to the gravitational landscape it travels through. As this river of stars sweeps through the halo, its path is subtly perturbed by the invisible clumps of dark matter and the gravitational wakes of other cannibalized dwarfs. By observing how the stream has been warped or painted across the sky over time, scientists can map the detailed distribution of mass throughout the entire halo, weighing the unseen dark matter component with a precision that no other method can provide. The existence of this Monoceros-like ring provides some of the strongest evidence for the hierarchical model of galaxy formation. It is a tangible, observable record of the fact that giant galaxies grow by consuming smaller ones, and that the halo is the permanent resting place for the debris from these ancient feasts. This single structure connects the past to the present, showing us that the majestic, ordered spiral of Andromeda we see today was built upon a foundation of cosmic violence, its final form sculpted by the gravitational ghosts of galaxies that are no more. Floating through the immense darkness of the halo, far from the brilliant spiral arms, are immense and ghostly structures that are not made of stars, but of the raw, unfinished material of the universe itself. These are high-velocity cloud complexes, colossal accumulations of neutral hydrogen gas so vast they can contain enough material to build millions of stars, like our own sun. Their name comes from their observed motion. They are not simply drifting, but are plummeting toward the galaxy at incredible speeds, often hundreds of kilometers per second. Their journey is a slow-motion cosmic rainfall, a delivery of fresh fuel from the intergalactic void directly into the galactic ecosystem. The origin of these falling giants is a subject of intense study, as they represent two very different chapters in the life story of a galaxy. One compelling possibility is that we are witnessing the galaxy feeding for the very first time. This gas could be pristine, primordial hydrogen and helium that has been floating in the emptiness of intergalactic space since the dawn of time, never having been processed inside a star. Over billions of years, the immense gravitational pull of Andromeda and its halo of dark matter has been steadily drawing this raw material inward. The high velocity we observe is simply the terminal speed of this intergalactic gas as it free falls into the galaxy's deep gravitational well. In this scenario, these clouds are the cosmic equivalent of a fresh water supply being piped into a city, providing the fundamental ingredients from which future generations of stars and planets could one day be built. The alternative origin story ties these clouds directly to the galaxy's violent past. They may not be pristine at all, but rather the shredded debris from past galactic interactions. When a small, gas-rich dwarf galaxy is torn apart by Andromeda's tidal forces, its stars are pulled out into long streams, but its diffuse gas reservoir can be stretched and fragmented into enormous clouds that continue to orbit independently. Similarly, a close encounter between Andromeda and another large galaxy, even if it did not result in a full merger, could have violently ripped gas out of their disks, flinging it into the halo, where it now condenses into these massive, falling complexes. In this case, the gas is not primordial. It carries the chemical imprint of its previous stellar generations, a recycled material being returned to the galactic system. Determining which of these stories is correct for any given cloud is a key goal for astronomers. By using radio telescopes to study the cloud's chemical composition, they can search for the telltale signs of heavier elements. If the gas is truly pristine, it should be almost purely hydrogen and helium. If it contains even trace amounts of elements like oxygen or silicon, it is almost certainly recycled debris from a galaxy that already hosted stars. Beyond their origin, the ultimate fate of these clouds is critical to understanding the future of Andromeda. They represent a potential fuel source for future star formation. For a galaxy to continue making new stars, it needs a steady supply of cold, dense gas. As these high-velocity clouds crash into the hotter, more diffuse gas of the extended galactic halo, they can be compressed and shocked, potentially triggering the collapse of dense pockets within them. Some of this gas may eventually cool, sink toward the galactic disk, and provide the raw material for new stellar nurseries billions of years from now. However, this journey is perilous. The halo is filled with the multimillion-degree plasma of the X-ray halo, and the intense heat and pressure from this superheated environment can evaporate the in-falling clouds, tearing them apart before they ever reach the star-forming disk. It is a cosmic race against time and temperature, where the survival of the cloud determines whether its material will ignite as new suns or simply be vaporized and added to the galaxy's hot, gaseous atmosphere. These high-velocity clouds are therefore more than just inert blobs of gas. They are dynamic players in the galactic life cycle. They connect Andromeda to the vast cosmic web of intergalactic material, while simultaneously serving as living fossils of its past collisions and acquisitions. Their study helps us understand how a galaxy gathers its resources, manages its fuel supply, and potentially secures its stellar future. Now we encounter an object that pushes the boundaries of what we can even call a galaxy, a specter in the halo known only by its ghostly gravitational pull. This candidate, our 24th strange object, possesses the mass of a substantial dwarf galaxy, yet when astronomers point their most powerful telescopes toward its location, they are met with a profound emptiness, a patch of sky that is almost completely dark. The primary evidence for its existence comes not from light, but from the subtle, telltale wobbles it imposes on the orbits of nearby, visible stars, and through the technique of gravitational lensing, where its mass warps the light from more distant background galaxies. This invisible titan seems to be a dark galaxy, a concept that sounds like science fiction, but is a serious proposition in cosmology, a massive, self-gravitating system that, for some mysterious reason, failed to light up with the fires of stellar birth. The debate surrounding this object strikes at the very heart of our theories of galaxy formation. On one side of the argument, this could be a pristine, fossilized relic from the early universe, a dark matter halo that managed to avoid one of the most fundamental cosmic processes. According to our standard models, galaxies form when dark matter clumps together, creating gravitational wells that draw in ordinary gas. As this gas cools, condenses, and fragments, it eventually ignites into stars. A true dark galaxy would be a system where that crucial second step never happened. Perhaps the gas within this halo was simply too hot to cool down efficiently. Maybe it was sterilized by the intense ultraviolet radiation from the first galaxies during the epoch of reionization, or its gas could have been stripped away by a close encounter with Andromeda before it had a chance to collapse. In this interpretation, we are looking at a cosmic stillbirth, a potential galaxy that never was, preserved in its embryonic, dark state for billions of years. The alternative explanation is more conservative, but equally fascinating. This object might not be a failed galaxy at all, but rather a particularly dense and isolated clump of dark matter that happens to have a handful of ancient, faint stars orbiting within it, stars so few and so dim that they are currently undetectable against the blackness of the halo. In this scenario, it is not a dark galaxy, but a star-poor or ultra-faint dwarf galaxy pushed to its absolute limit. The distinction is critical. A pure dark galaxy, completely devoid of stars, would be a revolutionary discovery, confirming that dark matter can indeed form structures on galactic scales without any accompanying visible matter. It would provide a unique, uncontaminated laboratory to study the properties of dark matter, free from the complicated astrophysics of stars and gas. On the other hand, if even a few dozen ancient stars are eventually found to be associated with it, the object would fit more comfortably, if still oddly, into our existing category of ultra-faint dwarf galaxies, just an extreme example of how inefficient star formation can be in certain environments. The intense search for a luminous counterpart to this gravitational phantom is ongoing. Astronomers are using the most sensitive instruments available, taking long exposure images in multiple wavelengths, hoping to detect the faintest possible glow from any stellar inhabitants. The outcome of this search has profound implications. If confirmed as a true dark galaxy, it would strongly validate the cold dark matter model of cosmology, which predicts that the universe should be teeming with a vast number of such dark subhalos surrounding large galaxies like Andromeda. Finding one would solve one piece of the cosmological puzzle, while simultaneously presenting a new one, understanding the exact conditions that can prevent a galaxy from ever awakening. This enigmatic presence in the halo, defined more by its absence than its presence, forces us to question the very definition of a galaxy and reminds us that the most massive structures in the universe can, in fact, be the hardest ones for us to see. Deep within the infrared sky maps of the Andromeda Halo, astronomers have pinpointed a true enigma, a brilliant, isolated beacon of heat that shines with incredible intensity in the infrared part of the spectrum, yet remains completely invisible to optical telescopes. This is our 25th strange object, an unidentified infrared source that appears as a single, blazing point of thermal energy, a cosmic ember glowing in the darkness with no stellar light to explain its origin. When a telescope looks at this location in visible light, it sees only the profound blackness of the halo, but when it switches its view to the infrared, a powerful source suddenly flares into view, telling us that something is there, something that is either generating immense heat or is so thoroughly cloaked in dust that all of its visible light is being absorbed and re-radiated as this tail infrared warmth. The nature of this hidden object is a compelling cosmic puzzle, and scientists have several fascinating theories, each pointing to a very different and equally spectacular kind of celestial engine. One of the leading possibilities is that we are looking at a superstar cluster in its very earliest, most embedded phase of formation. Imagine a stellar nursery of epic proportions, a single region where not dozens, but hundreds of thousands of new stars are igniting all at once, still swaddled in the thick, dark cocoon of gas and dust from which they were born. The prodigious energy output from all these infant stars would be almost entirely absorbed by the surrounding dust, heating it to high temperatures and causing it to blaze in the infrared. This object would be a proto-globular cluster, a future dense sphere of stars in the process of being built, hidden from our prying optical eyes by its own natal blanket. Its presence in the halo would be unusual, as such intense star formation is typically confined to the gas-rich disk, suggesting this could be the result of a rare, massive collision of gas clouds in the halo itself. A second, and far more exotic candidate is an object that until recently existed only in theoretical models, a Thorn-Zitkow object. Picture a truly monstrous hybrid star, a Russian nesting doll of stellar evolution. At its heart lies a dense neutron star, the collapsed core of a supernova. But this neutron star is not alone. It is enveloped by a massive, puffy outer envelope of a red supergiant star. The neutron star orbits within the belly of this giant, its presence drastically altering the nuclear fusion processes and the entire chemistry of the host star. The surface of such an object would be cool, making it very faint in visible light, but its interior would be a bizarre fusion factory, producing unusual elements that are dredged up to the surface, potentially creating a unique chemical signature and a strong infrared glow from surrounding dust. Finding one of these theoretical hybrids would be a monumental discovery, confirming one of the strangest predicted outcomes of stellar evolution. A third possibility pushes into even more speculative territory. Could this be the signature of an advanced extraterrestrial civilization? While this is the least likely explanation from a scientific standpoint, it is a fascinating thought experiment. A Type 2 civilization on the Kardashev scale, capable of harnessing the entire energy output of its star, might construct a vast energy harvesting structure like a Dyson sphere or a similar swarm of satellites. Such a megastructure would absorb stellar radiation and re-emit it as waste heat in the infrared, appearing almost exactly like the object we see, a point source of immense infrared emission with no corresponding visible star. While extraordinary claims require extraordinary evidence, and natural explanations are always preferred, the sheer strangeness of this source forces us to at least acknowledge the remote possibility that we could be looking at the engineering project of an intelligence far beyond our own. The continued study of this infrared phantom will require the most powerful tools at our disposal. Spectroscopic analysis of its infrared light could reveal the chemical fingerprints of the material around it. If it is a dust-enshrouded cluster, we might see the signatures of warm, complex molecules. If it is a Thorn-Zitkow object, its spectrum might reveal unusual abundances of elements like lithium, rubidium, or molybdenum, produced by its unique internal processes. By monitoring it over time, astronomers will also look for any variability in its brightness, which could help rule out or confirm certain models. Whatever this object ultimately proves to be, its very existence reminds us that the halo is a repository for the rare, the hidden, and the theoretical. It challenges our observational limits and dares us to look at the universe in a different light. revealing that some of the most powerful cosmic objects can only be found when we learn to see the heat they leave behind in the shadows. Now we turn our attention to a pair of gravitational predators locked in a final, lethal dance far from the galactic center. Evidence for our 26th strange object, a binary black hole system, comes not from a steady glow of light, but from the subtle, rhythmic wobble of space-time itself. While a single, isolated black hole is nearly impossible to detect, a pair of them orbiting one another creates a unique and dynamic signature. As these two massive objects spiral ever closer, they stir the very fabric of the cosmos, generating ripples known as gravitational waves. Sophisticated observatories like LIGO and Virgo are designed to catch these faint whispers from the universe, recording the distinctive chirp that signals the final moments before a merger. Alternatively, if this binary system is actively feeding on stray gas, the intense friction and heat within the accretion disk surrounding them can produce a brilliant, fluctuating source of X-rays, a telltale beacon of their violent partnership. The very presence of such a system in the halo, however, is a clue to a dramatic history. Stellar mass black holes are the remnants of massive stars, and such stars are born, live, and die in the dense, gaseous environments of a galaxy's spiral arms. So how did this pair end up in the sparse galactic outskirts? The most likely explanation involves a cosmic slingshot from a globular cluster. These ancient, densely packed collections of stars are like celestial petri dishes for creating exotic binary systems. In the crowded core of a globular cluster, complex gravitational interactions between stars are common. A black hole can find a partner, and through a series of close encounters with other stars, the binary pair can be hardened, their orbit tightening. During this chaotic process, a third object can act as a gravitational catalyst, absorbing energy from the binary system and being flung out of the cluster at high speed. According to Newton's third law, for every action, there is an equal and opposite reaction. If one star is ejected, the binary black hole system can receive a powerful kick in the opposite direction. In a sufficiently energetic event, this recoil can be strong enough to eject the entire binary system from the globular cluster entirely, banishing it to roam the vast expanse of the galactic halo as a celestial castaway. This isolated dance is more than just a curiosity. It is a precise laboratory for testing the fundamental nature of gravity. As the two black holes spiral inward over millions of years, the frequency and amplitude of the gravitational waves they emit increase in a very specific pattern, a pattern predicted by Einstein's theory of general relativity. By the time they are on the verge of merging, their orbital speed is a significant fraction of the speed of light, and the space-time around them is wildly distorted. The final chirp of gravitational radiation captured by our detectors carries within it the imprint of this extreme environment. Analyzing this signal allows scientists to probe gravity in its most powerful regime, testing whether Einstein's predictions hold true or if there are deviations that might point toward new physics. The eventual merger of this halo-bound pair will create a more massive, single black hole, and the properties of that final object, its mass and spin, will tell us a complete story about the properties of the two original black holes and the dynamics of their cosmic waltz. Every such detection adds another data point to our understanding of the population of black holes in the universe, helping us piece together the life cycles of the most massive stars and the dynamic processes that shape the stellar ecosystems within dense star clusters. This distant, dueling pair, hidden in the darkness, is therefore a key witness to both the violent interactions that can occur in stellar cities and the most profound laws that govern our universe. Streaking through the halo's darkness like a miniature quasar, our 27th object is a celestial paradox, a solitary neutron star that was violently ejected from its birthplace, yet somehow carries its own power source, blazing a trail of energy across the void. This isn't just a runaway pulsar, it's a cosmic engine, a kicked neutron star actively powering a pair of powerful, collimated jets that scream out from its poles at near light speed. The phenomenon is known as a microquasar, and finding one so far from the star-forming regions of the galactic disk is a discovery that challenges our understanding of how such systems form and persist. We typically find microquasars within the bustling disk of a galaxy, where they are locked in a binary dance with a normal star, siphoning material from their companion. So how does this lone wolf, this stellar exile, manage to fuel such a brilliant and persistent display? The secret lies in a cosmic partnership forged just before its dramatic ejection. The story begins with a binary star system, two massive stars born together in a dense cluster within Andromeda's spiral arms. The more massive of the two lived its life quickly and exploded as a supernova, its core collapsing into the neutron star we see today. That initial supernova explosion likely gave the system its first kick, sending it careening through its stellar neighborhood. But the system remained bound, the neutron star and its companion star continuing their orbital dance. Over time, as the companion star itself evolved and expanded into a red giant, the neutron star's immense gravity began to pull a steady stream of gas from its partner's outer layers. This stolen material didn't fall directly onto the neutron star's surface. Instead, it spiraled inward, forming a flat, superheated structure known as an accretion disk, a whirlpool of plasma orbiting at fantastic speeds. Friction within this disk heats the gas to millions of degrees, causing it to emit tremendous amounts of X-rays, while the innermost material, stripped of its angular momentum, plunges onto the neutron star's surface or is swept up by its powerful magnetic field. It is this process of accretion that powers the entire system. Some of the infalling material, instead of being consumed, is channeled by the neutron star's magnetic field lines and blasted away from its magnetic poles in two oppositely directed, narrow beams, the spectacular jets we observe. These jets, composed of relativistic particles, punch through the surrounding interstellar medium, creating glowing lobes of radio emission that can be detected across vast distances. The neutron star became a fully fledged microquasar, a tiny but formidable replica of the gigantic quasars found in galactic cores. The final act of its exile came when the companion star itself reached the end of its life and detonated as a supernova. This second explosion, occurring in a binary system that was already moving at high speed, was catastrophically asymmetrical. The sudden, violent loss of mass and the resulting kick effect were enough to completely unbind the system. The neutron star was shot out of the galactic disk like a bullet from a gun, while its former companion was either destroyed or sent flying in a different direction. What makes this particular object so strange and wondrous is that the neutron star did not leave empty-handed. In a fantastically rare turn of events, it managed to retain a portion of its accretion disk, or perhaps it was able to quickly capture enough material from the tenuous interstellar medium of the halo itself, allowing its jets to continue firing. We are therefore witnessing a ghost ship, an engine that was fueled in one place but is now running in complete isolation, its brilliant jets a testament to a partnership that was severed by a stellar cataclysm, yet whose power endures. This nomadic microquasar provides a unique laboratory for studying the physics of accretion and jet formation in an unusually clean environment, free from the complicated gas clouds and magnetic fields of the galactic disk. Its persistent glow tells us that even in the deepest, darkest frontiers of intergalactic space, the universe can still find a way to ignite the most brilliant and energetic of beacons. Nestled within one of the ancient globular clusters that orbit like lonely sentinels in the Andromeda Halo, there shines a star that simply should not exist. Surrounded by a vast population of ancient, cool, red stars that formed over 10 billion years ago, this star stands out like a brilliant blue sapphire in a sea of faded rubies. It is a blue straggler, a stellar anomaly that appears paradoxically youthful, hot, and massive in a neighborhood where every other star should have long since aged into stellar retirement. The term straggler perfectly captures its nature. It seems to be lagging behind in the evolutionary race, blazing with a vigor that its contemporaries lost eons ago. The mystery of how such a blue, energetic star could exist in a cluster where all stars were born at roughly the same time has captivated astronomers for decades, and the solution is as violent as it is beautiful. There are two primary, dramatic pathways to creating a blue straggler. The first is a story of stellar cannibalism within a binary system. Imagine two stars born as a close-knit pair, orbiting one another in a cosmic dance. As the more massive star ages, it swells into a red giant. If the stars are close enough, the smaller companion can begin to gravitationally pull material from the puffy outer layers of its giant partner, siphoning off hydrogen fuel and funneling it onto its own surface. This transfer of mass essentially rejuvenates the smaller star, giving it a fresh supply of hydrogen to burn in its core. It becomes more massive, hotter, and bluer, effectively resetting its evolutionary clock and allowing it to shine with a brilliance that belies its true age. It's as if a younger star stole the life force from its aging sibling to prolong its own prime. The second pathway is even more direct and violent, a head-on stellar collision. In the incredibly dense cores of globular clusters, where stars are packed together 1,000 times more tightly than in our solar neighborhood, close encounters are not just possible, they are inevitable. Sometimes, two lower mass stars can literally crash into one another, merging into a single, new, more massive star. This newly formed object, born from the wreckage of its progenitors, would have a larger reservoir of hydrogen fuel and a higher core temperature, causing it to shine with a hot, blue light that makes it appear as a youthful outlier amidst its ancient peers. This particular blue straggler in Andromeda's halo, however, holds an extra layer of mystery. Not only is it blue and energetic where it shouldn't be, but detailed spectroscopic analysis has revealed that its atmosphere carries a highly unusual chemical signature, a specific overabundance of certain heavy elements that defies standard predictions. This is the real puzzle that has astronomers intrigued. When stars collide or transfer mass, the violent mixing of material should produce a fairly predictable chemical outcome, homogenizing the elements from the two original stars. The strange fingerprints found in this star's atmosphere suggest a much more complex history. One compelling theory is that this blue straggler is not a second-generation object, but a third. It might be the product of a collision between two stars that had already been chemically altered by a previous partner. Perhaps one of the progenitor stars was itself the result of an earlier merger, already enriched with unusual elements, and then it collided with another star, creating a chemical cocktail that we are only now detecting. Another fascinating possibility involves the type of stars that merged. If one of them was already in a highly evolved state, nearing the end of its life, its interior would have been layered like an onion with different elements forged at different depths. A collision could have dredged up material from these deep, otherwise hidden layers, spewing elements like carbon, oxygen, or even S-process elements like barium out into the newly formed star's atmosphere. This would be like cracking open a cosmic geode. The outside looks ordinary, but the violent impact reveals a spectacular and unexpected interior crystalline structure. The presence of this chemically peculiar blue straggler provides a unique window into the dynamic and sometimes chaotic lives of stars within dense clusters. It tells us that these ancient globular clusters are not the serene, static retirement homes we once imagined, but are instead dynamic environments where stars can interact, merge, and be reborn in dramatic fashion. By studying its specific elemental abundances, astronomers can perform a kind of stellar archaeology, working backwards to unravel the sequence of events, the dances, the thefts, or the crashes that led to the creation of this brilliant, blue, and chemically enigmatic stranger in the ancient halo. Returning to the ghostly presence that defines so much of the halo's mass, we encounter an invisible structure that challenges the very rules we thought governed dark matter's behavior. This is an extended dark matter subhalo, a colossal yet diffuse clump of invisible mass that was detected, once again, not by any light it emits, but by the way its gravity subtly distorts the light from countless background galaxies in a phenomenon known as weak gravitational lensing. The mere detection of such a subhalo is a triumph, confirming the long-held prediction that galaxy halos should be teeming with smaller dark matter substructures, the leftover building blocks from the galaxy's assembly. But the properties of this particular subhalo are what make it a profound anomaly. When astronomers measured its size and mass, they found something deeply puzzling. It is far more spread out, or fluffy, than any of our standard cosmological models allow. Imagine expecting to find a tightly packed snowball, and instead discovering a wispy, diffuse cloud of snowflakes that somehow holds together over a vast volume. This object has a surprisingly low density. Its mass spreads so thinly that it defies the standard predictions of the lambda CDM model, the reigning theoretical framework that describes a universe dominated by cold dark matter and a cosmological constant. For decades, this model has been spectacularly successful at explaining the large-scale structure of the universe, from the cosmic microwave background to the distribution of galaxies. But it makes very specific predictions about how dark matter should behave on smaller scales, predicting that dark matter subhalos should be dense and centrally concentrated, their particles moving relatively slowly and clumping together efficiently under gravity. This fluffy subhalo, with its low central density and extended profile, simply does not fit that picture. It behaves as if the dark matter particles within it are somehow resisting being packed together as tightly as they should. The discovery of this diffuse giant forces cosmologists to consider some radical alternatives. One compelling possibility is that this observation is a clue pointing toward a more complex nature for dark matter itself. The standard model assumes dark matter is cold and collisionless, meaning the particles interact with each other and with normal matter only through gravity. But what if dark matter has some other, previously unknown property? For instance, if dark matter particles were able to interact with each other through a new force, a so-called self-interacting dark matter, this could provide a mechanism to explain the subhalo's puffiness. In this scenario, when dark matter particles collide within the subhalo, they could transfer energy and momentum, effectively creating an outward pressure that prevents the structure from collapsing into the dense core predicted by the standard model. It would be analogous to a gas. If you heat it, it expands. These self-interactions could be gently heating the dark matter from within, causing it to form a more extended, fluffy halo. Another, even more mind-bending explanation involves the quantum properties of the dark matter particle. What if dark matter is not a heavy, slow-moving particle, but is instead an ultralight particle, so wispy that its quantum mechanical waves are spread out over a scale as large as a dwarf galaxy? This concept, known as fuzzy dark matter, suggests that these wave-like properties would inherently prevent the formation of dense central cusps in small subhalos, resulting in the very kind of diffuse, extended structures we are now observing. This object, therefore, is more than just another invisible clump. It is a potential Rosetta Stone for decoding the fundamental physics of dark matter. Its existence and properties put direct, observational pressure on our theoretical models, forcing us to move beyond the simplest assumptions. The implications of this single, fluffy subhalo ripple outward to touch upon one of the most persistent problems in modern cosmology, the core cusp problem. For years, astronomers have noticed a discrepancy between the dense central cusps of dark matter predicted by simulations and the shallower, core-like distributions observed in many dwarf galaxies. This extended subhalo in Andromeda's halo provides one of the cleanest and most compelling pieces of evidence for this mismatch, as it is detected through gravity alone, free from the complicating astrophysics of gas and stars that can make interpreting dwarf galaxy observations difficult. By studying its exact shape and gravitational influence with ever greater precision, we are conducting a direct test of dark matter on a scale where the competing models diverge most dramatically. The halo, once again, proves to be the ultimate laboratory, a place where the invisible architecture of the universe is revealed not in the brilliant light of stars, but in the subtle, ghostly distortion of gravity itself. And now, we reach the culmination of our journey, a final object so perplexing it serves as a perfect bookend to the halo's collection of cosmic curiosities. Our 30th and final strange object is a star that refuses to follow the rules, a solitary sun whose light behaves in a way that defies every established classification. Astronomers have cataloged thousands of variable stars whose brightness changes in predictable, rhythmic patterns, pulsing with the steady beat of a cosmic heart, or dimming periodically as an orbiting planet transits its face. But this star is different. Its variations are chaotic, almost seemingly random, with a strange flickering on time scales from hours to days, superimposed atop a much slower, long-term dimming trend that has seen it fade significantly over the past century. It is an anomaly that simply doesn't fit when you try to force its bizarre light curve into the known categories of stellar variability, the Cepheids, the RR Lyrae, the eclipsing binaries. It rejects them all. It is an astronomical orphan, a star that appears to be playing by a set of physics we have not yet written. The initial, most tantalizingly speculative explanation that captured the public's imagination was the possibility of an alien megastructure. The idea, popularized as a Dyson sphere or a similar vast, energy-harvesting construct, suggested that the star's irregular dimming could be caused by a partially completed swarm of orbiting satellites, blocking its light in a complex, artificial pattern. While a fascinating thought experiment that reminds us of the vast possibilities inherent in the cosmos, this hypothesis is considered extremely unlikely by the scientific community. The incredible energy and material resources required to build such a thing, combined with the lack of any corresponding infrared waste heat signature that such a massive structure would inevitably emit, makes a natural astrophysical explanation far more probable. It's a fun idea to ponder, but the real answer is almost certainly rooted in new, undiscovered stellar phenomena. So if it's not aliens, what incredible natural process could be causing this star's impossible behavior? One compelling theory points to a cosmic smokescreen of epic proportions. Imagine the star is surrounded by a vast, chaotic disk of dust and rocky debris, the remnants of a cataclysmic planetary collision that occurred in the system's distant past. Within this disk, there could be immense, swarming clusters of comets or vast clouds of fine, opaque dust, all on wildly eccentric orbits. As these swarms and clouds pass between the star and our line of sight, they would cause the erratic, short-term flickering. The long-term dimming trend could then be explained by a slow, inward migration of the densest part of this debris disk, gradually building up a more permanent, diffuse shroud around the star. This would be a system in the throes of ultimate chaos, a place where the formation of planets went terribly wrong, leaving behind a lasting, dusty monument to the violence. Another, more exotic possibility involves the star itself being a bizarre, unstable hybrid. Perhaps it is a rare type of highly magnetically active star, where immense starspots, darker, cooler regions on its surface grow and decay not in regular cycles, but in unpredictable, continent-sized flares of magnetic activity. These dynamic spots, combined with powerful stellar winds that episodically eject shells of opaque gas, could create a complex, overlapping pattern of dimming and brightening that our current models simply cannot replicate. We may be looking at a previously unknown phase in a star's life, a brief, tumultuous period of magnetic instability that occurs only under very specific and rare conditions. A third, and truly mind-bending, theory suggests we are not looking at a single star at all, but rather a complex gravitational dance. The star could be a tight binary or even a triple system, where the stars are not only eclipsing each other, but are also encircled by a warped, precessing disk of gas. The gravitational tug-of-war between these closely orbiting bodies could cause the disk to wobble, its shadow flickering across our viewpoint in an incredibly complex pattern that would appear random over the short observational timeline we have. The long-term dimming could then be a gradual change in the orientation of this entire system relative to Earth, slowly bringing a thicker portion of the warped disk into the line of sight. This star, this final enigma in the halo, ultimately represents the frontier of our knowledge. It is a humbling reminder that for all we have learned about the universe, there are still phenomena that lie just outside the edges of our understanding. It challenges astronomers to develop new models, to think creatively, and to continue observing this celestial rebel until its secrets are finally unlocked. It stands as a perfect symbol for the Andromeda Halo itself, a realm of shadows and mysteries, where the ordinary rules break down, and the greatest discoveries are often the ones we cannot yet explain. Taken together, these 30 strange objects form a single, coherent story, a grand cosmic autobiography written in the language of stellar streams, dark matter clumps, and rogue stellar corpses. They are not merely a collection of random anomalies. They are the permanent record of the Andromeda Galaxy's turbulent and dynamic life, a testament to its violent, cannibalistic history. The overarching theme that connects a hypervelocity star stream, the ghost of a devoured dwarf, and a pair of tidal dwarf galaxy candidates is a narrative of hierarchical assembly. We see a galaxy that was not born in its current majestic form, but one that was painstakingly assembled over billions of years through a relentless process of mergers and acquisitions. Each stellar stream is a chapter detailing the destruction of a smaller system. Every rogue supermassive black hole is a scar from a past galactic collision. The very lopsided shape of the halo itself is the final, frozen splash from its last great feast. This evidence overwhelmingly supports the modern view of galaxy formation, painting a picture of a universe where growth is driven by gravity's relentless pull, a cosmic dance of construction through destruction that has shaped every large galaxy we see. Beyond chronicling the past, these halo objects serve as one of the most powerful natural laboratories we have for testing and refining our most fundamental theories of physics and cosmology. They are the proving grounds for our ideas about dark matter, that mysterious substance that makes up the bulk of the universe's mass. The discovery of an ultra-diffuse galaxy seemingly devoid of dark matter forces us to question whether all galaxies must be anchored by this invisible scaffold. The fluffy, extended dark matter subhalo challenges the standard cold dark matter model, suggesting that dark matter particles might interact with each other in ways we never anticipated. Even the gravitational phantom of a potential dark galaxy pushes the limits of our definitions, asking us what the minimum requirements are for a structure to even be called a galaxy. These are not abstract philosophical questions. They are concrete, observational puzzles that the halo presents, and their solutions will fundamentally alter our comprehension of the universe's hidden architecture. The halo is equally critical for advancing our understanding of stellar evolution under the most extreme conditions. A runaway pulsar or a nomadic microquasar gives us a front-row seat to the high-velocity dynamics that can eject stellar remnants from their birthplaces, allowing us to study the intricate physics of neutron stars and their jets in pristine isolation, away from the complicating glare of the galactic disk. The brilliant, chaotic variability of our final, unclassifiable star pushes the boundaries of what we know about stellar behavior, hinting at undiscovered phases of magnetic activity or the aftermath of unimaginable planetary system collisions. Even a blue straggler in a globular cluster, a star that seems to defy aging, reveals the dramatic, transformative power of stellar interactions and collisions in dense environments, showing us that the lives of stars can be far more complex and eventful than our textbooks once suggested. Ultimately, the value of exploring this cosmic frontier extends far beyond satisfying our curiosity about our nearest galactic neighbor. The Andromeda Galaxy is often called a twin to our own Milky Way, and by studying its halo, we are effectively reading our own galaxy's future. The processes of accretion, merger, and dynamic ejection that are so clearly recorded in Andromeda's outskirts are undoubtedly occurring in our own backyard, albeit from a perspective that is impossible for us to see directly. The structures we map and the phenomena we catalog in Andromeda's halo provide the template for understanding the origin, evolution, and ultimate fate of our own cosmic home. They teach us that galaxies are not static islands, but vibrant, evolving ecosystems, constantly being reshaped by both their internal engines and their violent interactions with the wider cosmos. Every strange object we find is a crucial data point, a piece of evidence that helps us move from speculation to knowledge, refining our grand models of how the universe works on the very largest scales. What an incredible journey it has been, traveling through the shadowy frontier of the Andromeda Galaxy's halo to uncover 30 of the cosmos's most peculiar inhabitants. From the ghostly whispers of invisible dark matter clumps to the brilliant, chaotic flares of unclassifiable stars, each discovery has revealed a new layer of complexity in our galactic neighbor. We've encountered the phantom remnants of devoured galaxies in vast stellar streams, witnessed the cosmic exile of runaway supermassive black holes, and marveled at the serene beauty of planetary nebulae glowing in utter isolation. These aren't just random curiosities. They are the vibrant, dynamic population of a region we once mistakenly thought of as empty and quiet. The halo is far from a static wasteland. It is a living, breathing archive, a cosmic library where every strange object is a volume in the grand history of Andromeda. This sprawling spherical cloud is the ultimate record of creation and destruction, a testament to the violent mergers and relentless gravitational dances that built the majestic spiral we see today. It's a place where the conventional rules of astronomy are constantly challenged, pushing us to develop new models and question our most fundamental assumptions about dark matter, stellar evolution, and the very nature of what constitutes a galaxy. Each object, from the hypervelocity stars to the dark matter-deficient ghosts, serves as a critical data point in our quest to understand not just Andromeda, but the universal processes that shape all galaxies, including our own Milky Way. So, the next time you find yourself under a clear, dark sky, take a moment to gaze toward the constellation of Andromeda. That faint, fuzzy patch of light is more than just a distant island of stars. It is a galaxy teeming with mystery in its outer darkness, a reminder that the universe's greatest wonders often lie in the places we least expect. We would love to hear which of these 30 strange objects captured your imagination the most. Was it the solitary supermassive black hole cast adrift, the brilliant and unpredictable variable star, or the haunting echo of a long-vanished dwarf galaxy? Share your thoughts in the comments below, and let's continue this cosmic conversation.